Hi class, let's talk linear algebra. Today we're going to talk about properties of the basis. Properties of a basis of a vector space. In particular, we're going to be exploring the ideas relating bases spanning linear independence. So in terms of the setup, say V is a vector space. And the dimension of V is equal to n. Remember, that means that there exists a basis of size n for the vector space V. Let's start talking about Theorem 24. This is going to come in 7 parts. This video will include parts 1 through 3, and then 4 through 7 will be in the next video. Part 1. Say we've got a random collection of vectors, Vn, and they span V, as in every element of V can be expressed as a linear combination of V1 through Vn. Then, any collection of vectors that's bigger, say W1 through Wm, where m is greater than n, then any such collection of vectors is going to be linearly dependent. For this theorem, we're not going to write down every single proof in excruciating detail, even though you can definitely reconstruct the proofs from what I'm about to say. For now, I'm going to give you the ideas of these proofs. So we've got V1 through Vn, and they span V, which means that all of the Wi's can be expressed in terms of the V's. So I'm going to use some notation for this. So one of the W's is going to be some sum of the V's with some kind of coefficient, right? And I've labeled it so the K tells you which vector V it's attached to, and the J tells you what vector W it's attached to. So what we get, actually, if we're trying to talk about the linear dependence of the W's, as usual, we're going to get some equation that looks like this. The CI's, of course, are reals. Now let's actually use our sums. So each W is going to be expressed in terms of some sum of the V's. A sub m, k, vk, k again goes from 1 to n because there are n of the V's. All right, we're going to re-express. And this might require some thought, but we're going to gather this all into a single sum, and then we're going to switch the sums. So we're going to have a sum over the VKs, and the coefficient of each VK is actually going to be another sum. And here we can see these guys are the new coefficients for an expression of 0 in terms of the VKs. Okay. But remember, the VKs are linearly independent. So this sum is going to be 0 for all k. Let's take advantage of this, okay? So what we have is this thing. How many of them do we have? Well, we have 1 for every k, so k goes from 1 to n. These are the coefficients of the V's. And so this is a system of equations where the CJs are the unknowns. Remember, we're trying to figure out if the C's, the coefficients, are 0 or not, in order to tell whether the W's are linearly independent. So, how many unknowns do we have? We have m unknowns. What are the unknowns? The CJ's. Then we have n equations. What are these equations? A, J, K, Cj is equal to 0, J equals 1 to n, and we've got 1 for each K from 1 to n. Okay, m unknown, n equations, where m is greater than n from the get-go. So this is going to be an underdetermined, homogeneous system. And by an old result, there exists a non-trivial solution. C1 through Cm. Okay, so we've got non-trivial solutions that solve all of these equations, and that this means that there's a non-trivial solution to this equation. So the W1s through Wm's are linearly dependent. That's the end of the idea. Let me just remind you what we proved. Fact, V1 through Vn, if we've got a spanning set for V, and we've got W1 through Wm, another set of vectors where the number of W's is greater than that spanning set, then these are going to be linearly dependent. Why do we like this fact? Well, let's explore a little bit about what this allows us to do. So, question that I might ask you are 1, 2, the vector 3, 4, and the vector 5, 6 in the Euclidean vector space of dimension 2, are they linearly independent? You could set up your equation with coefficients and then prove that those coefficients have to be 0 or can be non-zero. Or you could use the fact that we just proved. We know that two vectors, 1, 0 and 0, 1, already span R2. So 1, 2, 3, 4, and 5, 6, because there are more of them than the two above, these are going to be linearly dependent, because there are 3 of them. Simple. All right, let's continue. Theorem 24, part 2. Say V1 through Vn and W1 through Wm are bases for some vector space V. Then they have to be the same size. We're not going to prove this rigorously, but I do want to leave you with the idea. Both are linearly independent. Both sets are linearly independent because they are bases. So by 1, bases, remember, are also spanning sets. And since all of these have to be linearly independent, by 1, n has to be less than m, because if it were less than or equal to m, because the W's form a spanning set. And so if the V1 through Vn's are going to be linearly independent, they have to be less than or equal to M. But similarly, the other way around, M has to be less than or equal to N. So we get equality. Awesome. Why is this useful? What does this allow us to do? Well, I want you to crawl something. So 1, 0, and 0, 1 as a set. And then we also have 1, 3, 2, 4 as a set. And we know that the first set is a basis for R2, the standard one, and the second set you proved was a basis for R2 last class. So these form bases for R2, as you know. What Theorem 24 Part 2 allows us to do is to understand that it is not a coincidence that these have the same size. It is not a coincidence that both sets have the same number of vectors. Bases have to have the same number of vectors, no matter what vectors make them up. And so we can turn to something like this, 2, 4, 1, 2, 4, 2, 1, 3, and just by eyeballing it, we can say that these cannot form a basis for R3. Because a basis must have 3 elements, like every other basis, like the one that we're familiar with. All right. Theorem 24, Part 3. Any set of n linearly independent vectors spans V. Again, let's talk about the idea. Say V1 through Vn is the linearly independent set that we're talking about. And just to remind you, n is going to be the dimension of V, our vector space, which means that there is a basis of that size. So, by 1, V1 through Vn, and then you add on a Vn plus k, is going to be linearly n plus 1 is going to be linearly dependent by 1. So, where did this vk come from? This vn plus 1 come from? Well, it's any vector. Any other vector in the space. So, V1 through Vn, tacking on Vn plus 1, must be linearly dependent by 1. What linear dependence means is that such an equation that I'm going to set up, this is going to be 0. And we'll note the C's aren't going to be just the zero vector, because linear dependence. And also note that Cn plus 1 itself cannot be 0, else this same equation is going to show that V1 through Vn are linearly dependent. Okay, so given all of that, what we're going to do is solve. We're solving for Vn plus 1. So we get C1 V1 plus Cn Vn divided through by Cn plus 1 is going to be Vn plus 1. And so Vn plus 1 is in the span of V1 through Vn. And since Vn plus 1 was any vector, that we know that the span is all of V. There's the idea. Again, what does this allow us to do? Okay. This tells us that to find a vector space, to find a basis for a vector space, we need only check linear independence. So, for example, if I were going to ask the question, does 1, 2, 2, 3 form a basis? Well, let's make a matrix out of it, and we're going to take the determinant. We know that this determinant is 3 minus 4, which is minus 1, which is definitely not 0. So 1, 2, and 2, 3 are linearly independent. And we know that the dimension of R2 itself is 2 because it has a basis 1, 0, 0, 1. Okay. So what we've shown is that we've got a set of the right size made of two vectors, 1, 2, and 2, 3, and we've checked that they're linearly independent. By this part of our theorem, we know that 1, 2, and 2, 3 form a basis. Basis for R2, because they also span R2 by Theorem 24, Part 3. You're going to have a lot of practice using these. For now, I want to continue the work of proving and looking at and using Theorem 24. Next lesson is going to do Part 4 through 7.